CLI and a cross-platform IDE for C and C++. Download now.
Hi everyone, my name is Dmitrii Radivonchik, and today I'll be giving you a talk titled Writing C++ Code is Challenging and Writing Performant C++ Code is Daunting. So without further ado, let's jump straight into it. So the research that I'm going to be providing to you today is going to be based on an open source project called Desbordante. More in the project itself later, but I would like to express my gratitude and acknowledge everyone in the team who worked in their spare time to make the project happen and contributed a lot of their lifetime to that project to actually achieve and be in the place where it is at right now. So I'm not going to read out every name on that list, but trust me, everyone on that list contributed very meaningfully. So my talk today is going to be focused on performance in C++ and how we're going to be, basically it's going to be a case study that we've done in Desbordante that has to do with how students approached implementing various algorithms. So let me start. So it's been for the past few decades, C++ has been kind of the default language for anyone or any entity, that team that wanted to write some project or some code that would actually be performant and that is performance sensitive, that it needs to process large quantities of data in a short amount of time. And the reasons, there's a lot of reasons for that. So it's a high-level language. It's very expressive. It's feature-rich, especially nowadays. It's compiled to native instructions, so it's not interpreted. It's compiled straight into the thing that runs on your CPU, and it unlocks the full CPU potential. It provides you access to all the tools and all the technology that CPU has in it. And there are a lot of supporting examples of this statement. So there are full industries that kind of rely on that language for their performance, finance industry being one of the most prominent examples, probably, at least for me. I come from that industry. But yeah, machine learning, image recognition, embedded, all of those areas make heavy use of C++ for performance-related tasks. But performance in C++ does not come without the drawbacks. So there's when you get such power, something has to give. And in case of C++, there's again a whole list of things that kind of give. C++ compared to some other languages is harder to develop in. So it takes more effort to write code that will work correctly and be safe. It's harder to maintain for kind of the same reason. It's harder to use for prototyping things, so just spitting out something that will kind of work to see that the project is actually progressing. And it is known for being less safe than other languages, which is one of the, I guess, very prominent problems of the language. Given the pointer arithmetic and direct access to stack, and I don't need to tell you that, there are safety problems in C++. And there are a lot of alternatives, obviously, depending on what you want to do. But C++, the name of the game in many cases is performance. So with C++, where we arrive at with this is that it is optimized for performance gains. It gives you the full control over the CPU, but it comes at the cost of other things related to software development. And so if you're willing to pay those costs, you would expect to get the benefits, right? So in this case, what I'm trying to say is that if you've built something in C++, then you would kind of expect that it just performs well and probably performs better than the same thing written in other languages. But actually, let's see if that holds in reality. So here where Desbordante comes along. So Desbordante is a Spanish word. It's Spanish for boundless. And it's actually an open source tool for mining complex patterns in data efficiently. So it's got 62 contributors. It's got 468 stars on GitHub. It's written in C++ 17 because it was started in like 2019. It is science intensive. So what does this mean? There are several types of data patterns you can be mining, and there are simple data patterns and there are complex data patterns. And science intensive here means that it's actually aimed at mining something very meaningful. So it usually has to do with a lot of computations on the entire data set that you have in mind. And there are lots of types of complex patterns of data. So to give you some examples, those are functional dependencies, order dependencies, unique column combinations, so on and so forth. It's a wide array of those things. And one thing about Desbordante that is quite interesting is that it is, while it has some senior members of the team that are kind of overseeing the project and dictating the direction that it goes in, the most of the code is actually written by students that study at the universities, and yeah, they do that to write their theses and like their reports that they need to do throughout the education process in the universities, and so it gives us an interesting project developed in that way. And the idea of Desbordante is comes from the following fact, from the following story. So there's an existing project called Metronome that is built in Java that implements a wide array of algorithms for mining all sorts of complex data patterns in data, and it is kind of the ideological inspirer of Desbordante. But the thing about Metronome is that it's been picking up the kind of this direction of the developing those algorithms has been picking up some popularity in recent years. But the tool itself is built around, it's focused on the prototyping the algorithms and trying them out, and on the process of developing the algorithm itself. Once the algorithm is implemented, it is there, it's available in Metronome, but it's not necessarily optimized for the actual appliance of the algorithm. So the tool, in the end, the tool is built for developing algorithms, not necessarily applying the algorithms, even though it kind of does give you this opportunity and ability to apply those algorithms. So the idea of Desbordante was to kind of bridge the gap between the real use cases of those algorithms and the implementation and the research done around those algorithms. So the idea is that some research showed that Metanome's poor Metanome's poor performance, runtime performance, limits the sizes of data sets that it can be ran on, and limits the amount of algorithms, the number of algorithms you can actually run on those data sets, because it's just going to take too long. And actually, some other drawbacks of Metanome is that it takes a lot of effort to set up, even for people with technical background. But if researchers or whoever wants to try to actually run those algorithms is not going to necessarily be able to go through the entire process of setting up Metronome to try things out. So Desbordante aims to bridge that gap in both in terms of performance and in terms of ease of use and setup. So the solution at the time when the project was started was to write Desbordante in C++ so that we can have access to all those amazing features that have to do with performance. But yeah, there are also other benefits, like it's available as a Python package, as a web version, and yeah. And that gives us an interesting mix. So the performance is the key quality of Desbordante, because that just comes from the idea of the thing. But it's mainly developed by students, and every time those students do something there, it's normally either writing some new algorithm from some research paper that actually developed the algorithm, or improving or optimizing an existing algorithm in that already exists in the code base. And every time they do that, they write extensive reports that they need to kind of provide as a proof of their work. And that those reports, they're basically, not like research papers on entry-level research papers, let's say. And so those research papers have all sorts of interesting and useful information, like the the process of decision making, or like the limitations, and most importantly the measurements, of the algorithm or optimization that was performed as part of that work. And each paper is thoroughly supervised and reviewed by senior people. Yeah, and it describes everything that has to do with the body of work that they've done. And yeah, so when I say data set here, I mean the body of those papers and their corresponding pull requests on GitHub. So basically, a lot of those papers describe how students approached optimizing some existing algorithms. So here on the screen, you can actually see like one student first implemented an algorithm, and then the next semester they were basically trying to optimize that algorithm. Yeah, and one of the things that this data set provides us the ability to do is to look at how they approached the optimizing those algorithms, and what was the key point of them actually being able to optimize it or not be able, and whatever is the result. And that is since the data set is quite diverse and quite big, that just allows us to have a bird's eye view on that process. Yeah. So the goal of my talk today is to show you, and so we're going to focus on the stories where people were trying to optimize the algorithms that they've previously implemented in the project. We'll take a look at what kind of techniques they used, what worked, what did not work. We'll try to explain why things worked or didn't work in each particular case. And also at the end, we're going to take a look at how all of that compares to Java and what kind of interesting insights we can draw from this. So I'll note, I need to note something about the numbers. So we're going to have a lot of measurements here. But obviously, whenever you see any measurements or any numbers, everyone should ask themselves kind of where do those numbers come from and what do they actually mean? So all of those measurements come from the actual papers, and like the papers that students wrote as a report of their job, and they always contain measurements. And normally, so obviously it's like across those papers, details might vary, but most of the time it's like around 10 runs of each thing, and they either build confidence intervals or take just the average depending on like the variance. And they're all taught on how to do those measurements in a better way. So the operating system caches are cleared, swap is disabled, CPU frequency is fixed, and we are focusing on just the algorithm time only, so we're not including any sort of parsing of data and so on and so forth. So yeah, here's the table. That's kind of fast. That developed fast, because here's the table of that has some representative number of like a representative set of algorithms that were first implemented in Desbordante and then optimized. And it basically lists how well the optimization ended up working. So on the left, you have the names of the algorithms. Then on the x-axis, you actually have the speed up, and that is a logarithmic scale here. And then we have for like obviously performance of any given algorithm is going to depend on the data set that it is applied to. And all of those measurements are done on a number of data sets, not just some one data set. And so in order to understand those lines that I've drawn here, it's basically the left line is the minimal improvement. Well, in this case, it's the speed up between the optimized version of the algorithm and the base version of the algorithm that was implemented in the first case. Like initially. So this is the minimal speed up that was achieved on all of the data sets that were considered. On the right side is the maximum, and the middle is the median. So it's not the average, it's the median. And as you can see from that graph, so here's the line that delineates 1. So that means like we haven't moved anywhere. And as you can see, the results and the success is varying. Like there are some algorithms were able to optimize themselves very very well. Some did a decent job. Some were like okay, and some kind of, and they didn't necessarily fail, but didn't yield the results that we would expect them to yield. And so that actually each of those lines on this graph represent a story of how people tried to optimize. They tried something, they looked at how it worked, and they've recorded all of that. So I've went through all of that, and I'm gonna be highlighting some of the stories and trying to find some patterns across those stories, and I'm gonna basically explain them to you. Yeah, so I've prepared several cases that we're gonna dive deep into today. Oh, kind of deep. And then now I'm gonna go through those cases. So the case number one is, I called it death by 1,000 copies, and it's kind of the most obvious one. So there was an algorithm called DES, and that is basically, it's mining some numerical association rules in the data. It was implemented by a student, and then it was integrated into the platform, and already outperformed the reference Java implementation like sixfold. But then on the next semester, they did a quality pass on that code, and they tried to kind of refactor it and just, make it look better and interoperate with the rest of the platform better. So they did some changes, and the code got shorter. And they're at the end of this, there was lesser code than in the beginning. But then when they did the measurements to prove that they did not break anything, they found something quite interesting. So yeah, they along the way, they basically applied some basic principles of C++ hygiene. Whenever they could, they used the move semantics. They would pass parameters by constant references. And yeah, they were applying those basic techniques, like reserving the vectors when they know the size that they're going to grow into in advance. Yeah, so no rocket science here. But then when they measured, so yeah, this is an example of what they would do, like before, after. Like they would give here we obviously have an extra copy, and here we just move it and do not copy it at all. Here, yeah, the vector example is also kind of obvious. Like we're just filling the vector here. It's going to get resized in the process multiple times, so reallocated. And if we just reserve it in advance, it's not going to get reallocated. So that's nice. But what they got after they measured it was quite interesting. So old DC, so in this graph, you can see the runtime, like the execution time comparison between the old and new version of the algorithm. So the old version, like the new version, outperformed the old version quite significantly. So it was at least 6.5 times on each of the data sets that they have considered. Yeah, on the bottom, you can see is the names of the data sets. So small abalone, big abalone, small cancer, big iris, huge iris. Yeah. And the memory consumption on each of them was same or lower. So what's interesting about this is that they were not trying to optimize the code. They were not trying to apply any complex techniques. They were just trying to apply basic things, basic hygiene in C++, and that ended up yielding such a huge runtime improvement. Yeah, so that might be quite interesting and quite unexpected, especially for students. So it wasn't that the initial code was kind of badly written or something. So the initial code was structured quite well already. It worked. It outperformed the Java already, and it was properly integrated into the platform. They just did a little cleanup, and that's where it ended. So yeah, the key lessons, key takeaways from this case is that the unnecessary copies can compound, and all those unnecessary operations can yield very significant slowdowns. And you got to be on the lookout for those things if you want your code to perform well. So the case number 2, I called it the wrong tool for the job, and we'll see why. So there was this algorithm called order that basically was looking in a tabular data. Think of an SQL table, right? So if there's an SQL table and it was checking for each X and Y, it was trying to find such pairs of sets of columns X and Y that for which the following condition holds. Like if all of the columns are sorted on this set of columns X, then it must be sorted by on the columns Y. Yeah, and so when they just rewrote that algorithm from Java, so Java has all the code available, and they just basically did the same thing as the Java code was saying and wrote it in C++, and implemented it in the Desbordante platform. They already got a speed up of up to 9x and a median speed up of around 3x. And here's the graph. So that's kind of what you see here. But you can see that some data sets, particularly this diabetes data set, C++ was actually showing worse results than Java. And so the author decided to profile their code to see what's happening and why is that. So they went ahead and they found out that basically the flame graph is going to look very different depending on whether you find those pairs of X and Y that I was explaining earlier that we're actually searching for, or you're not going to be finding them. So in case of, yeah, basically if the output that if the dependencies that you're going to find is going to be like an empty set, so no dependencies in that data set, then most of the time is going to be spent in the initial sorting. So you can see here it says sort on that flame graph. So it creates sorted partitions and sorts them. So a lot of time spent in that sorting that we just used like std sort. And on figure 2, you see the runtime for a data set that has a lot of dependencies. So the output size is going to be big. And in that case, actually the created single sorted partitions takes up small fraction of the time, but the most of the runtime is going to be in compute dependencies. And that has a lot of hash table operations in here. So here, hash table operations, and here. So they looked at that and they realized that the containers that they were using, the standard template library containers like standard std and unordered set and unordered map, like they were taking up, the operations in those containers were taking up a lot of time on that flame graph. And so they decided that they're going to try to replace those containers with some more specialized containers. And since though they are so hot, since they're node based, which means basically means that adding and removing an element, and each element in those containers is going to be a separate allocation. So it's going to be in some random, more or less, location in the memory. For that reason, it's basically not cache friendly. And yeah, when you do a lot of operations with those containers, when your nodes are scattered all over the memory, your prefetcher and your CPU caches are not going to do a very good job for you, and you really want to take advantage of those prefetcher, like of the of the service that the caching and prefetching gives you. So the optimization that they applied in this case was to replace first of all, replace the sorting function with the flat stable sort from boost. So as you remember, in one of the two cases that we've considered in the beginning, I mean, yeah, in one of the two flame graphs that we looked at, the majority of time was spent in that sorting. So if you can improve that sorting algorithm, that would probably improve the runtime. And then for the second flame graph, they decided to replace the standard template library containers with some quote unquote better or more optimized versions from Boost library. So they replaced the unordered set with unordered flat set, unordered map with unordered flat map. And both of those containers, both the flat set and flat map, use open addressing. That's when in your hash table, instead of having buckets and like a list of items that they refer to, they basically the entire data in the entire container just takes up some contiguous area region of the memory, and all the items in that region are, yeah, they basically reside in that contiguous piece of memory, which is much better in terms of cache friendliness and prefetching. And yeah. And so once they applied those optimizations and did the measurements, it basically showed that some of them didn't make big difference, but some of them made quite some difference. So here you can see let me explain what that table actually means. So basically the author tried all three optimizations separately, right? So they had a lot of versions of C++ code. Like they had the base version, the version with the flat map, then the version with the flat set but no flat map, and then the version with sorting but no other things, and then everything combined. And when they did the measurements, they found out that depending on the data set, the performance improvement that you would get varies basically. Is there a question? Because I'm seeing some. Okay, should probably continue. Sorry. I was seeing some Zoom reactions pop up on the bottom left. Oh, bottom right. Yeah, so basically we saw that on one of the data sets, flat set alone gave 5x improvement, and then everything combined gave consistent improvement across the board and like very considerable improvement for one of the data sets. One more example of that same thing is basically this FADA algorithm that was searching for inclusion dependency discovery. Yeah, when they they wrote the code and then they were trying to optimize it, and then they profiled it, which is always a very good practice. And they identified two hot hash tables. One of them was write heavy and the other one was read heavy, right? So on one of them, there are a lot of write operations, and the other one is dominated by the read operations. So the author decided that they'll just look up some online benchmarks of different third-party hash table implementations and looked like those benchmarks are gonna basically they contain the information about which hash tables perform better with which sizes, with which access patterns, so like write heavy or read heavy. And they decided that they were going to use em hash 7 for read heavy hash table and em hash 2 for the write heavy one. And then when they, so here's the table, they were comparing the C++ implementation against the Java implementation, and then the C++ implementation with em hash 7 and 2 in place against the Java implementation. And they've got quite a consistent improvement across all the data sets. So basically, yeah, here on the bottom we see the improvement, and here on the top we see the table of runtimes in seconds per data set. So like Java on metronome for this TPCH 10 took 448 seconds to complete, and with C++ with em hash only took 302. So that yielded 1.48x improvement in runtime. So there are a couple of interesting things to devise from that table. First of all, is that the em hash actually improved things across the board. So again, that's an improvement. But then that the unordered map, actually on one of the data sets, it didn't beat Java at all. Like it beat it by 1 second, which is quite interesting, right? Because you would expect C++ to be generally faster than Java, but here is an example where they actually meet each other. Yeah. So the takeaway is basically, there are a couple of takeaways here. First of all, is profiling is a very good practice that allows you to identify the hot places in the code, and it can basically give you information on how it's best to optimize your code. And then understanding access patterns to your containers is very helpful. And it might be a good idea to look up some benchmarks, either third party or any benchmarks that you have access to make some educated guess on what's going to be better. But that does not save you from profiling. You have to profile still. Yeah, and the standard containers that are node-based are cache and friendly, so you might want to replace them once you're trying to optimize your performance. Now, the third case, I called it the simmed marriage. So SIMD is single instruction, multiple data, right? And we basically, there were two separate parallel attempts in Desbordante to make use of that. And they led to different outcomes. So I thought that was really interesting and decided to show it to you guys. So DFD is one of the algorithms that searches for functional dependencies in the data. And when they implemented the base version, they profiled the base version and realized that the bottleneck of the when I say base version, I mean just ported whatever Java was doing to C++. And they realized that this minimize function, we don't need to understand what it does, just minimize function, is the bottleneck. And that minimize function does a lot of checks on bit subsets. So basically, there's like bit set A and bit set B, and it verifies whether B is subset of A. Well, I'm not sure if that formula is correct here, but anyway, yeah. So, and each of the bit sets was represented by boost dynamic bit set. The idea was that they were doing a lot of those operations. So they were like, yeah, we can try to take advantage of SIMD in here by loading 4 of those bit sets into an 256-bit register, and then basically doing that operation in one instruction. So in theory, they should have gotten like a considerable speed up, 3x, 4x speed up. But when they actually did the comparison, the performance comparison, the result that they've got was that the maximum observed speed up was only 3%. And for the most data sets, it was actually like not even relevant at all. And bear in mind, again, all of that was happening in the function that was the hottest in the entire thing. So it's not like they optimized the parameter loading or something. They actually were trying to optimize the hot thing. It just, the optimization that they tried did not do anything. So here on the bottom, you can see the runtimes of the sequential C++ version and the vectorized, so the one using the single instruction, multiple data C++ version. And yeah, basically for most data sets, as you can see, nothing has changed. And it barely changed for like breast cancer data set and hepatitis data set. So it did change a bit, but yeah, not much. So we should probably ask ourselves, why did that happen? Like in theory, that should work nicely, right? We were doing what we would otherwise do in multiple instructions in just one. So that's nice. But what we have to realize is that those bit sets, so they were dynamic bit sets, and so each bit set is a separate heap allocation. So they were actually scattered across the memory. They were not in continuous region of memory. And so the bottleneck there was not actually computing those things and not performing the actual bit set operation on like once the data is loaded into the registers, it was loading the data into the registers. And so when we replaced the instruction with the SIMD instruction, we optimized the wrong part of that hot path because it was actually starved for data. It was not starved for compute. So now we'll take a look at FIDA. It's an algorithm that has already shown up in one of the previous examples, and it is actually done by the same author. So the same author had bared with their idea to make use of SIMD. And in this algorithm in FIDA, they are basically processing rows of data one by one. And the author realized that if you batch those operations, so you process not one row at a time, but if you batch them together, then you can be processing multiple rows at a time, and those rows will actually be in the continuous memory regions. And so this time around, the SIMD might actually do something for us. So they first implemented buffered or chunked processing. So they read data in blocks and were processing it in blocks. And that allowed them to finally have access to continuous region of memory with that data. Yeah, the problem was that they were actually calculating some hash functions of the data in those in those rows, and the hash function involved the rotate left instruction. So that is when you take the register and you basically rotate it left, and any bits that are sticking out from the left side go to the right side. So the AVX2 instruction set doesn't have a native rotate left function for packed 64-bit integers. So AVX5 does have it, but AVX2 does not. So that meant that they had to basically emulate that one instruction with 3 separate instructions. So that reduced the theoretical 4x improvement of like doing work of 4 instructions in one down to just one, like 30%, because they were doing the work of 4 instructions in 3 instructions. So that's less promising, but still worth trying. 30% is a good improvement. And so let's see if it worked. So now this table here is their measurements. And the way I've structured this table is that on the left, basically there's some string describing the implementation that they're using. And then there's a number of data sets in here. For each data set, we provide the runtime and the speed up compared to the previous row. So we're able to track how each next row is different or better or worse from the previous row. And the idea here is that the base implementation, the thing on the top is the metronome implementation. So that's Java. Now, the next thing is C++ baseline. So that's just having ported what Java does explicitly, straight to C++, let's say. Then they applied the custom hash tables. That's the em hash 2 and em hash 7 examples that I have given earlier. Then they tried, on top of that, they added buffering. So like the chunked processing. And on top of that, the next row is all of that plus simd. So we can see basically how each next layer of optimization improved or not improved the runtime. And what we can see here is that, well, the custom hash tables we kind of looked at earlier, and they did a good job across the board. But then the buffering did amazing job, actually. So in some cases, it would add only like 16, 17%. But for most other data sets, the improvement would be quite significant. So 38% here, 74% here, 63% here, 62% here. So that can be explained again by prefetching and better cache locality, basically. So they would like be pulling data from memory and would be like it would prefetch more stuff, more data than you actually need at the moment, just hoping that you're gonna access that next bit of data in the next instruction, and the buffered processing actually gives you that. It kind of aligns with that pattern of fetching data from RAM. And then the SIMD on top of that, it did not, in some cases, it did not provide amazing improvements, but it was kind of consistent across the data sets. And one of the data sets benefited the most. It benefited to 17% out of theoretical 30%. So that is quite good. But again, unlike the previous example where our maximum was 3, that is a better improvement across the board. So yeah, the contrast basically is in DFD, the data layout that we were working with was scattered heap objects. In FIDA, we had continuous buffered arrays. And so our cache behavior in DFD was like basically we would miss on every load and we would have to reach out to RAM. And on FIDA, we're prefetcher friendly. So that means that the data that we're going to access is already in L1 cache. So that's nice. And the synth game there was like no more than 3%. And on FIDA, it's actually meaningful. So the conclusion that I'm trying to arrive at here is that SIMD is not a magic wand. It's not going to just speed up everything that you throw it at, but it's a magnifier. If your memory access pattern is already good, SIMD can improve that, but it's not gonna just fix your problem for free, basically. Case 4 is I called it the law of the instrument, and this is quite funny. To a man with a thread pool, everything looks like a parallelization problem. So that the idea here is that parallel processing can be a very powerful tool for speeding up some computations or any operations, right? But my idea is that, or not my idea, but my point here is that you have to be very precise with how you apply it. And C++ is great for parallel processing, right? So it has a lot of functionality, a lot of library functions, a lot of support. So that's great, and gives you access to most low-level features that you can access in theory with your CPUs for taking advantage of that threading of your multiprocessing CPU with multiple cores. So we had number of 5 algorithms, different algorithms that tried parallelization, and we can kind of take a look at all of them and see what worked and what did not work. So let's see. Here's a table. On the left, you see the names of the algorithms. So for HYUCC, there are actually two, like they parallelized in 2 ways, let's say. So they had basically 2 separate versions of parallelized code. So that's why it's mentioned 2 times in here. And some of those algorithms we have already discussed previously, like order and theta. Yeah, and so the interesting thing is that, again, I was trying to look at the best improvements and the worst improvements. And one pattern is that the worst improvement is almost always worse than the sequential, than that of the sequential version. And then the best is like, it depends, right? So there's order that did not achieve much, even in the very best case scenario. And then there are others that basically achieved some degree of success. So yeah, there are some notes in here, but I'm not going to be probably reading them out. Yeah. So let's see. Now we're gonna dive into each one of them and try to understand what exactly happened. So why is the difference so big, and what this tells us about this whole approach, basically. So for DFD, the parallelization there was highly dependent on how wide your tables are. So if we're talking about SQL tables again, for a data set with 30 columns, it would actually spawn 30 independent tasks, and the parallelization would work well. And for 9 columns, apparently 9 tasks is not sufficient to overcome the thread overhead, and so it just became slower. Yeah, so that teaches us so that the benefits that you should be expecting from this are highly data dependent. For HYUCC, the parallelization increased variance in the results. Some cases became much faster. In some cases became slower. And that was already, the result that we saw there was already after author having iterated on what kind of granularity of parallel processing to work with. So they actually tried parallelizing very cheap operations that are like subset comparisons, and that turned out to be very bad and was worse across the board. So they did not even include the measurements in the final thing. So now FIDA, it actually had a different problem that sometimes you can basically do the map and reduce approach that HYUCC took along. So like you basically divide your data set that you need to do some computations on into pieces. Then you do process those pieces in parallel in multiple threads, and then you kind of aggregate the results. So for FIDA, that did not work, and they basically had to introduce some sort of interlocking between the threads, and the interlocking itself, depending on the data, would slow down or speed up the processing. So that's another example of like high variability data dependent implementation, which is beneficial in some cases, but not necessarily beneficial in other cases. And so for order, what happened there, that's the example when our max improvement was 1.14, so 14%. What happened there is that author did not realize that in most cases, the processing was going to stop just after like very quickly, basically. And so that's an example of where the parallelization was not applied at the right level and in the right place, and that did not yield the expected results. And the takeaway here is that it's important to understand that parallelization, while in all of those cases it provided some or like moderate success or even great success, it always comes at a cost, and there are lots of costs to parallelization. Again, the code becomes much harder to maintain, to reason about, to modify, to debug, to analyze, and at that point, once it's there, like there are a lot, like once you implement parallelization, once you employ that, there are a lot of things that can go wrong. There are a lot of things that can silently break, and you're not necessarily gonna notice them. So, for example, your performance can become worse because of some cache bouncing, right? Even if you're using like atomic operations, not mutexes. Yeah, and there are a lot of things to consider. Also, you have to be very smart about the granularity at which you basically divide the data and then process it. Because if you pick that wrong, then your overhead on threading is gonna overcome the benefits of actual parallel processing. And yeah, it's data dependent, and it also depends on the algorithm. Not all algorithms even allow for parallelizing. So Amdahl's law is basically the bigger the higher percent of your program has to be sequential, the fewer results you'll see from parallelizing it. Yeah. And the last case that I wanted to talk about is no C++ knowledge needed. What does this mean is that, yeah, let's take a look and then draw some conclusions. So Pyro is a functional dependency discovery algorithm. The idea there is that their FDs are functional dependencies. So the idea is that it's basically trying different, like taking a look at different candidates for functional dependencies, and then tries to reason which ones of them are actually holding on data and which are not. And the candidate set is huge. It's n times 2 to the power n, where n is the number of, I think, rows. So that is a huge number. Oh, must be columns, sorry. Yeah, so that is a huge number. And so those candidates, all of those candidates have to be checked. And basically there's operation in the process of search, like it's a huge search tree that needs to be searched. And there are a lot of different algorithms that employ different pruning strategies, like basically that narrow down the search that they're performing and try to reason like whether a functional dependency can be built from those columns or those columns based on what they have seen so far. And this particular algorithm has to do with basically something that might resemble dynamic programming. So it's it's partition based, which means that basically the information that you've acquired from checking one of the candidates can be reused for checking other candidates. And you kind of combine them together, like you intersect them. So you've checked two functional dependencies, and then that can tell you something about their intersection and so on. And so the computations that you do with this partitioning are costly. They're performed a lot in this algorithm, and their results are reusable. But given how many of them you perform, so the natural idea here is to cache the results, right? But the problem is that you're performing so many of them that you cannot possibly cache all of them. So you have to decide which ones you're going to cache and which ones you're not going to cache. And that is going to actually affect your performance a lot. So yeah, that I know this is a complicated setup, but yeah, I guess I hope the idea is clear that you have to decide what to cache and what to not cache. The original algorithm, so the paper that basically the authors of the algorithm itself, when they wrote the research paper that defined the algorithm and explained it there, they used a coin flip to decide whether to cache a particular dependency or not. And then when they would run out of memory or be close to that, they would just randomly prune half of the cached entries. And that caching did still work. It improved it's much better than not to cache anything at all. But the idea that students came up with in Desbordante is to actually be smart about what you cache and what you do not cache. So the idea is to introduce some mathematical metric to estimate how likely a partition is to be reused. And then they basically made this into a research paper that got published and accepted to a conference. It's ABDIS 2019. So that was a great result. Yeah, they basically used some two existing metrics. They introduced a novel metric. Then they modified very slightly the algorithm to actually not use a coin flip to decide whether to cache a thing, but to use those metrics. and then they did the measurements. And on some data sets, the results are not that significant, but for some bigger data sets, you can see that the results they've gotten is almost like half the runtime. So that is a great result. And that required very few C++ changes, actually. So that's really nice. So that, yeah. Let's take a look at another example. That is a similar one, let's say. So GFD mining, another example, another algorithm. It was implemented in the platform and it worked correctly, so it was doing the right thing. But then it was kind of slow. The author had the feeling that it was kind of slow. So they ran perf and they generated the flame graph and they looked here. And basically you can see that the satisfied function in here, it was basically generating a ton of candidates and then checking a ton of candidates. And the satisfied function, which checks the candidate, is very red. So it's very hot. And the idea that they've gotten was that maybe they were generating too many of those candidates. Yeah, basically they looked at some other algorithms in the same field and looked at the parts that have to do with candidate generation and those algorithms and just implemented it there. And what they arrived at was a huge improvement in runtime. So what started off as like taking a couple of seconds or like, yeah, fraction of a second ended up just taking a couple of milliseconds. And that was not any C++ optimization. It was just changing the algorithm to do a better job. And then you won't have to think about like simd or prefetching on any of that. And then your algorithm is going to be significantly faster. One more last example of this is myFD algorithm. Oh, I have a typo here. Well, anyway, yeah. It's posted. It's actually. It was actually also posted in a research paper, and it's indexed by IEEE. Yeah, they implemented some algorithmic improvements, and they were able to achieve crazy speed ups of like 200x essentially over Java or baseline C++. If you're interested, you can check out the link. Yeah, so the takeaway here is that if your algorithm is inherently slow, no amount of C++ magistry and magic can save you from that. So if the best improvements are always brought by improving the algorithm itself and not necessarily the code around it. So whenever you're trying to optimize anything, you have to keep that in mind. You have to consider whether you can actually improve the algorithm beneath it and not focus on those low-level details first. Yeah, once you've improved the algorithm, you can then start improving the details, let's say. So yeah, now this concludes the cases that I wanted to kind of consider. And I wanted to show you a graph of how we're actually comparing to Java. And I think there are some interesting things to be seen here. So that is a big graph. Again, that doesn't not all of the comparisons that we have done in the project, but this is a big number that I decided to put here. And it kind of shows an interesting picture. So let me explain the graph first. So on the left, again, you have the names of the algorithms. The ones with check marks are the ones that we have kind of covered in the previous cases. So those that do not have check marks have not been touched on at all. Yeah, and then for some of the lines, you can see that there's like a more prominent line and a fainter line. So the fainter line is basically it's the initial implementation or initial porting of the algorithm from Java to C++. And then the more prominent line is the actual the best implementation that we've got. So the one that is optimized. So for example, for HYMD, we had an implementation and then we basically improved it. And so the prominent line is the improved version and the faint line is what we had in the beginning. But not all of the algorithms were improved upon. Some of them were just ported and that's it. So like Tane, for example, like this doesn't have a faint line. So just like the best we've got is this. And again, on the x-axis, you see the speed up. That is a logarithmic axis. So like this goes up to like 250 improvement, really nice. But as you can see, the picture again varies a lot. So some of the algorithms were really impressive in how we were able to optimize them and how much they can actually beat Java. Some were less impressive, but still good. And some were questionable. Um, I guess there are two points that I'd like to point out here. Let's start with this guy. So here, the HYUCC, it generally beats Java quite convincingly. So again, the median improvement is like along the lines of 15 or 20 or something, right? But then there are some cases the minimal is actually below Java, so it's slower than Java. And that actually the like the thinking is that if it's able to beat it so consistently and by such a large margin, then it probably isn't necessarily an inherent problem with the C++ algorithm itself, right? So how come that Java is able to find back so efficiently in some cases? So let's take a look at that. So if you've ever tried to profile a Java program, or like we've tried to profile a Java program for this project, and in many cases, this is what you see. So like there's not a lot of info. This flame graph kind of tells you both everything and nothing. So it tells you that the problem is JIT, because the things that take up most of the runtime are JITted away. And JIT is short for just-in-time compilation. But then it tells you nothing because actually you don't know what those calls are. They were completely compiled into the native code. So JIT, the idea of JIT is that Java is generally interpreted, right? So you have JVM that interprets the instructions, but then when it detects in runtime that some functions are really hot and are called a lot, spend a lot of time in them, and then it tries to compile them into the actual code of into the native instructions of the processor and tries to call them. And the idea is that it's able to do all of sorts of things. So it avoids the unboxing and boxing drawback. It avoids it does devirtualization. So it just like it's cuts straight to the point and just executes the instructions. And that can be really, really effective in some cases. So for HYUCC, if you look at the performance comparisons, you can see that for absolute majority of cases, again, this is a logarithmic scale on the left, and those are data sets on the bottom. The C++ implementation was able to beat the Java implementation like convincingly. But there's one data set that is quite different, and that is the FD reduced 30. So the author actually wanted to understand what is happening here and why is metronome faster than C++ in here. So they looked at the flame graph and they realized that it's basically one very hot function iterating over huge amounts of data, because you can see that the runtimes are the highest for that data set. And that is exactly what JIT is good at. It basically compiled that function to native instructions and probably never missed, it was able to devirtualize what even C++ was not able to devirtualize. And it ended up being just better than, faster than C++ implementation, even though we have no reason to assume that C++ implementation is broken in any way, but it's just one data set that it actually gets outperformed by by Java implementation. And now the last thing I wanted to touch on is what about the bottom? Like what happened here? And that's kind of circling back to the point of the topic, to the point of the talk, is that we believe that there's something wrong about our C++ implementation of those algorithms, and that's why they're getting beaten by Java so convincingly. So this is basically work in progress. So that actually concludes what I wanted to tell you about today. Here are some links to Desbordante. So here's the GitHub. You can install it in PyPy, and there's a web interface that you can access, and you can even supply your own data sets to run some discovery algorithms on them. And all the papers, all the works by the students that I mentioned in this talk are available in the repository itself under docs/papers. And remember, performance is not granted, but it's absolutely achievable if you're willing to investigate. That's it for me today. Thank you.